Hello, this is Tom. Um, welcome to our YouTube video covering the material in the next installment of our Science and Christianity class. Today we have Matter and Quantum Mechanics Part 1. We're going to have at least one additional part. So welcome, and let's start today with some Bible verses. First of all, Hebrews 11:3 in the NIV says, "By faith we understand that the universe was formed at God's command, so that what is seen was not made out of what was visible." Now, I like this verse because there are several ways we could take it, and I'll leave it to you to reflect on, uh, you know, what the meaning is in general. But um, one way you could take it is to think that God made everything we see out of nothing, which I believe. But another way we can think about this verse is that everything that is made, every tree, every person, every building, every machine, the sky, um, the land, everything we see around us is made out of things that are too small to be seen with the naked eye. And so that's part of God's design. So the verse reminds me that God made things we see out of things we cannot see in that sense. And then the next verse is a favorite. It's Genesis 11:6. Um, Actually, this verse is taken from the account about the Tower of Babel found in that chapter of Genesis, um, which involves the human race getting together to do something contrary to God's will for them. And so the Lord does not approve of what they are doing. But there's one little nugget here that kind of tells us something valuable, which is a general thing. And I'll just read the verse. It says, "The Lord said, if as one people speaking the same language they have begun to do this, then nothing they plan to do will be impossible for them." So, um, you know, in context, they are actually in this chapter. The people are trying to build a high tower all the way into heaven. Um, um, God seems to suggest here. The Lord seems to suggest that um, He has He has given such capacity to the human race that literally, if we put our minds, that we can literally do anything if we put our minds together and if we're able to communicate and be in unity in one accord. So, um, you know, that can be a bad thing if we're trying to do something rebellious, um, that kind of defies God. It can be a good thing if we're trying to serve God and to serve one another. So I like both of those verses. Um, but I'm going to apply the second verse to the first case now. What we see in this chapter is how it is that those things we can't see, that make up all the things we can see, got kind of figured out at the beginning of the 20th century thereabouts, and how incredible um, it is that God made us with minds and abilities to kind of to kind of put that puzzle together. And as we go through today's class, keep an eye on all the collaboration involved here. No one person figured this stuff out. It was in the collective that humanity has figured out what we know about these things at this point. So welcome again to the class, and I'll go on. Just a quick um, review of last time. We had just seen that after 200 years of advancement in physics and chemistry, starting with Newton, uh, we have Maxwell's theory of electromagnetism, which kind of crowned classical physics. It built on top of the physics of Newton, um, um, math to describe electricity, magnetism, and light, showing that light was an electromagnetic thing. Now, that better understanding of electricity and magnetism had a lot of practical consequences and began reshaping everyday life. It opened up all kinds of possibilities that we are just now achieving today. Wireless communication, but also has for the last 100 years enabled radio. Well, that said, the period we find ourselves in um, is very much affected by all these developments. It's a time when practical chemistry has started to give people greater control over matter than they've ever had before. And a practical understanding of electricity and magnetism has helped the human race start to harness a fundamental force of the universe. So during this time, industry went nuts. There were many inventions. Some were odd, but whole new technologies grew up from nothing. Um, all the technology helped more and more scientific exploration to be done. People were able to do experiments and to see what could be seen with the new technology. It was a very dynamic period in the history of science and technology. It was such rapid progress. It felt like a new modern era had dawned. Um, and remember, this is on top of um, all the things that have happened to change society and to change individual lives that people often call the Industrial Revolution, or even the first Industrial Revolution. All this new stuff happening is really a second Industrial Revolution, and all of it is very dependent on the science of Newton and then Maxwell. Um, Physicists even talk about um, so much being figured out that there's really not much else to do. We saw that last time. There was the famous quote by Michelson. Nevertheless, there were some loose threads. Well, last time we dealt with one loose end. Um, One of the things that we were able to determine from Maxwell's equations was the speed of light. In fact, we found that light was an electromagnetic wave that came right out of those equations. But the interpretation of what that speed of light was relative to was fairly unclear. Finally, as we found out, Einstein said, well, gee, what if we just take Maxwell literally and suppose that everyone sees light moving at this speed, c, this large velocity c that comes out of Maxwell's equations, regardless of their relative motion. And we saw what happened. Time, space, matter, and energy end up being different for different observers. We find out that matter can be converted into energy and vice versa. We find out that past, present, and future, while depending on the particular observer, in some ways are more durable than ever before, because my future is someone's past, and my past is someone's future. So in a sense, it's not gone. It's still a future reality for someone. So past, present, and future seem to stay around forever. And we talked about the block universe in that regard. So the resolution of this one loose end from last time, to the extent we've talked through it, shook the foundations of physics to their core. Well, further loose ends remained. Chemistry at this time was going absolutely gangbusters since Dalton figured out that atoms existed. And we get to Mendeleev and how they're seeing that the elements hold to a certain pattern in terms of their properties, and they're figuring out, in practical ways how to exploit the laws of chemistry. But no one knew what atoms were or why element properties repeated in the pattern seen. Here's another loose end. Why did the elements absorb and emit specific frequencies of light? We talked last time about how if you take something like, say, hydrogen, it gives off only certain wavelengths of light, or it can absorb only certain wavelengths of light. So if you look at hydrogen that's been heated up, you end up getting an emission spectrum, like on the left, which you can split up by prism. So the combined color would probably be kind of purplish, but you pass it through a prism and you see these very specific lines. It turns out that, and this is new, it turns out that there was a mathematical pattern there that was able to be figured out. People noticed little bits of the pattern. Eventually, they all got combined into this thing called the Rydberg equation, and it was able to describe all the lines of the spectrum that could be seen for the leftmost column in the periodic table: hydrogen, lithium, sodium, potassium. So that seemed very, very intriguing, but still no one understood why. Well, here's another loose end. The entire world was on the verge of being electrified. And, in large, dense cities like Manhattan, that led to extreme nest of wiring slid between electrical poles like we see on the left. But here's the thing. All this is happening, but no one even knew what an electrical current was. No one understood what flowed, how charges flowed through a conductor, and yet the whole world was being electrified. Another loose end, it had been shown that magnetic fields could be generated by electrical fields. Maxwell's equations had been able to explain that. Yet permanent magnets were still a complete mystery. No one knew why a bar magnet exhibited magnetism. No one knew why the Earth was a huge permanent magnet in space. So those are remaining mysteries. Then we continue to have to wonder, okay, if the force we talked about so much last time, the electromagnetic force, which includes magnetism as well as the Coulomb or electrical force between charges, if that force is so much stronger than gravity in everyday life, how come we barely notice it at all? So there's a loose end we might want to explain. And also during the same period of time, and this is a new topic for us, we haven't talked about it, but radioactivity had been discovered and was a real loose end because no one understood it. No one knew what that was either. So at the turn of the 20th century or so, we have a lot of big questions and not any easy answers. In fact, they don't even know enough how to do a direct, straightforward experiment to kind of answer these questions. So what we're going to see, and this is characteristic of science, what we're going to see today is how the process of science unfolds. And because people do investigate what they can pose questions for, and things they can figure out experiments for, to get answers for those questions, those smaller questions, those more specific questions, as the process of science unfolds, as people do their research and they do experiments trying to explain all these things, eventually there's enough light being shed on the big questions so that people are able to start homing in on answers. So just kind of pay attention to that today, because I think we'll see plenty of evidence of that, and on into next time. So um, given that we're going to look at, basically across the board what's happening in science around this period of time, and we're not going to have to look at everything, because I know the things that kind of are necessary for us to map out the larger story. But we're actually going to pick up with electrical discharge. So, we've talked about static discharge before, including lightning, that kind of thing. But the term electrical discharge even includes cases where you could have an electrical circuit and you could have discharge across it. So we're going to start there today, and it may seem like a pretty humble place to start, given all the bizarre stuff we talked about with time dilation and the block universe. So it seems like a humbler topic, but it's going to set us on the way to wrap up the loose ends that we need to wrap up. And eventually we are going to get to some new exciting places, and we're going to encounter some disturbing new questions that we have to look into. So plenty of fun ahead. Okay, so let's start with electrical discharge. Okay, so what is electrical discharge? Well, as I mentioned, it can include things like electricity, or lightning or static electricity. But it can also include things like arc welding, which is something invented in 1809. You can see that in the little picture on the bottom right. If you have a big enough current running through, or if you have a big enough potential difference or voltage, and a small gap, the current can jump over it and basically create what we would call a plasma today, and you can actually do welding and things with it. So arc welding. I don't think at this time they fully understood it, but that was a practical application. Also, there was arc lighting. The picture to the left of that one shows a similar gap. If you put enough of a voltage across the two different sides of an arc light, electric arc light, it would create just a huge ongoing discharge as long as you maintain the voltage, and create an extremely bright light, which sometimes were, I think they were used in large plaghouses in places like London and things. Very bright, intense light. Before, Edison's lights were available. Beyond those applications, as the world's electrifying, it also turns out that electric discharge is a generally important topic as well, because if you have enough voltage difference between 2 points, you can get a discharge. It may depend on the geometry, like the shapes of the objects. It may depend on how far apart they are, and it may depend on the humidity, or just the whatever separates them. Even if there's an insulator between them, there can be a discharge if the voltage is enough. And all those things are important to consider. When they're electrifying, they need to understand, are they able to do what they're doing without having an unintentional electric discharge occur sometimes, which could be very damaging. It's kind of like artificial lightning striking. It can do a lot of harm. The particular voltage, under whatever situation, under whatever circumstances it is that causes this arcing, this discharge to occur, is called the breakdown voltage. So if you have enough of a voltage, a potential difference, You don't need a conductor, like William Gray showed would allow current to flow. The current is going to flow even without the conductor if it's a big enough voltage. And that brings us to Geisler tubes. There was a physicist and glassblower who first created these, and they were built specifically to study electric discharge. Um, Typically, these would be filled with like some trace gas, like hydrogen or nitrogen or whatever it was, and sealed off. And then you could put a big voltage across the two sides, and you could see, one thing you could see is what is the breakdown potential? How big does the voltage have to be before you can start to get a discharge? But beyond that, you can study the discharge itself. What was its behavior? So all this stuff was interesting to scientists at the time, and you could study some more things. But first, let me ask you a question. Are you guys ready to go tubing? Okay, because here we have a Geisler tube. Well, it turns out tubes are very important in the story of modern physics. All kinds of tubes, all kinds of tubes are going to be used for all kinds of reasons. And we're going to talk about a lot of those tubes today. And I just pause here to say, um, you know, uh, don't get your head turned around by the different kinds of tubes. We're going to talk through them. We're going to try to understand them. And we're going to learn what we can learn from them. I'll try to make it clear, but, you know, um, it would be easy to let them run together. So try to differentiate your mind as much as possible, and I'll try to explain it as well as I can. All these tubes on the screen are things that we're going to discuss today, or just barely removed from it. So a lot of tubes here. You might even recognize a few familiar kinds of things, um, like most of us um, in the class have been around long enough to know about vacuum tubes. There's a whole little set of vacuum tubes over on the right. So whereas today we use integrated circuits and we use solid state electronics like transistors and diodes and things, in those days they used vacuum tubes. And because these tubes allowed them to create circumstances where they could control the currents in some specific way, whether they were building the consumer electronics of the day, like the radio set that we see the back of on the left, or whether they were doing scientific exploration. So tubes are very important in the story of physics. Let's go tubing. Well, back to Geisler tubes. So one of the foremost things that Geisler tubes would do is glow when there was a discharge going on. If you put a particular trace gas in the tube, so basically you would try to vacuum out whatever normal air was in there and just put like a little trace of whatever gas you wanted. If you put that gas in the tube, you could actually see the um, the gas is glowing according to whatever their characteristic emission spectrum was, which we've talked about. But it's a very handy way to study the spectra. Um, and as I said um, earlier, you could use a prism to separate out the individual lines of color that you would get from those gases. So it's a great way to study these different gases and their spectra and everything. The examples on the right, by the way, are modern examples. We still use Geisler tubes to illustrate um, the specific spectrums of different elements. They can get pretty fancy. People back in the day when these tubes were invented um, um, saw them as a way to achieve various artistic expressions. And so they went kind of crazy. There are museums to these things now. Here, I mean, they started in 1857, but by the turn of the century, they'd gotten pretty elaborate, some of them. I will say, just in passing, that lots of spin-offs to these tubes. Not only are we going to see they were invaluable in the research in physics going on, during this period of time. But eventually, and you can see it easily in the example to the left, eventually this is where neon lights come from. They're a little bit different than Geissler tubes, but very similar. And then we also have fluorescent lighting today that is a direct descendant. It's also different because it doesn't, it's not as simple as these things. We have X-ray tubes, and we're going to run into Crookes tubes and other gas discharge tubes today, but they all started with Geissler tubes. So this is like the great grandfather of them all. Well, back to the Geissler tubes. There was a scientist named Crookes who noticed something subtle. He noticed something subtle, and here's a picture of a modern Geissler tube that will enable us to see, what he saw. If you look, you will see that on one end of this tube, it's very difficult. It's kind of hard to see. You can see that on one end of this tube, it's not really as bright as the rest of the tube. It's almost like the light, there's a little bit of a back glow, but it's almost like it takes the light a little while to get started. Okay? And he noticed that. Now, you wouldn't think that was very important, but you'll see how this all opens up. So he decided to try to understand what was happening there. Okay, so Crookes, he built some tubes, basically Geissler tubes, but he tried to make sure there was a better vacuum. So he wanted more of a vacuum, less gas, even a trace gas. So he wanted to achieve a higher and higher vacuum. And as it happens during this time, vacuum tubes or vacuum pumps are getting better and better. So that kind of helped him out. And what he found was, as you got to a higher vacuum, it took longer and longer and longer for the light to start glowing. Okay. And if you had a good enough vacuum, the tube would barely light up at all. Okay. But something still was happening because the glass on the end of the tube would start to glow. Okay, so something was causing the glass to glow. So let's look at this tube. Over on the left, like near the picture of Crookes there, over on the left we have what we call the cathode, okay, which is like the negative side of the circuit. And over on the right, you don't really see where it hooks up, but kind of 4/5 the way to the end, you have kind of a metal thing sticking up, which is where the positive side of the circuit is hooked up. Okay, and that's the anode. And it just so happens that in the picture there's a little cross on the anode, which fits with our Science and Christianity focus here. But the actual voltage that's applied between those two sides of the circuit, the cathode and the anode, are enough to pull the current along. Now, they don't really understand this. Remember, they don't understand what's flowing, but it's able to create a discharge. They knew that discharges occur. If the potential is enough to create a discharge, it's able to cause the discharge even with basically a vacuum in the tube, and yet something is causing the glass to glow on the end. And in fact, whatever that something is, it's casting a sharp shadow, like that cross in there, which is a stylized cross that they actually used during, Crookes actually used during his experiments. It's called a Maltese cross. You can actually see a very sharp cross cast. So there's something that's going from the cathode to the end of the glass that's just going right past that positive anode there, and casting, causing the glass itself to light up in a very sharp picture, with the kind of the cross there as a shadow. So the cross is intercepting whatever's coming from that cathode, and then whatever's coming that's not being intercepted by the cross just ends up slamming into the glass, causing the glass itself to glow. And they had no idea what this was. They had no idea. Um, it didn't seem to behave like light at all, because light is actually, as we found out last time, a wave. Um, Light doesn't, it would not normally achieve these kinds of really sharp edges in a shadow. There would always be kind of a, kind of a blurring that occurred on the edge of a shadow cast by light. And so something else was going on here. Something was coming from that negative end, that cathode, flying past the positive anode and slamming into the glass. And they called those things cathode rays. Cathode rays. They had no idea what it was. People immediately started suspecting that, since they generally thought that currents involved some sort of flowing charges, not that they knew what they were, they started to theorize that, hey, maybe this is a charged particle. Maybe these cathode rays are made out of these charged particles that are what flows when you have an electrical current flowing, but they didn't really know. It wasn't long before somebody put a magnet up to one of these things and saw that they could actually change the behavior of the cathode rays, to kind of distort or change where they hit the glass. And so it was looking better and better, like a charged particle. But this is a key experiment. Now, following him, we have scientists, not often talked about much these days, but he did something really key. He studied Crookes' work about the canal rays, and then he found something very, very interesting. He found that if you put holes in your cathode, which maybe we could call channels, which in German or Italian sounds like canal. If you put holes there, in addition to the fact that you would end up with canal rays hitting the glass at the end of the tube on the anode side, which is where the positive was, in addition, you could also see that there was something flowing in the other direction, right? Something was flowing in the other direction toward the cathode from the direction of the anode, and would actually pass right through and cause a glass kind of downstream from that to flow. Okay, and you could actually see these streams going through. And now these rays were found to be positively charged versus the canal, or the cathode rays, which were found to be negatively charged. So they could be affected accordingly by a magnet. And so they didn't know what they were. Okay, but it was fascinating. The color probably gave off the color given off would have been whatever the color was of the trace gas that was put into the Geissler tube. Now, he had a colleague, Wien, who went one better. He figured out a way to, on the end of the on the end of the circuit where the cathode was, which is where the so-called channel or canal rays were coming through, were also called the anode rays because they're coming from the direction of the anode. He figured out a way to use electric and magnetic fields so that he could bend anything making up those anode rays, unless it was moving a particular speed. And he was able to relate the speed to the mass of the of whatever particle it was that was making up the anode ray, or also called the canal ray. And what he found, when he had a hydrogen as the trace gas in his Geissler tube, what he found is that the mass of the particle that was coming from the from the direction of the anode through the holes in the cathode, the 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 when hydrogen was the trace gas, the mass was just what the chemist knew was the mass for the hydrogen atom, with to a very high precision. That held true for other trace gases. So he was able to figure out that basically these were atoms that had a charge. So apparently they had lost something, and they were left with a charge. They had lost or gained some kind of charge, so they had a net positive charge, and it was basically that type of atom. And you could see the characteristic spectrum, you could weigh it, and you could find the weight. So this was, so if you had hydrogen gas, you would get hydrogen, what we now call hydrogen ions. If you had another type of gas like oxygen, you would have oxygen ions. And in fact, this idea is going to be extended later on, to even build a way to analyze chemicals. Like you probably see in crime shows and things, how these days we can analyze just traces of chemicals. We can put them into a machine, and we can, well, the machine works like this. It breaks the sample into lots of little pieces, and kind of ionizes them. In other words, causes them to be charged. Then it passes them through this kind of arrangement here, and it's able to tell what all the little pieces are in terms of their mass. And from that and other things, they are able to pretty much analyze anything today. So this was the beginning of that concept, but it also gave an insight into a fundamental thing that was just starting to be understood. Well, that brings us up to J.J. Thomson. Okay, he built something called a cathode ray tube to study, yes, you guessed it, cathode rays. So this is up to about 1897. So these cathode rays have been discovered by Crookes, and what he did was he extended the Crookes tube a little bit. He played some games, kind of like Wien was playing. He used some electric and magnetic fields so that he could tune them and cause them to force the cathode rays that were coming through to hit a certain part on his little phosphorus screen that he put on the end. So he coated, actually, or it was a phosphorescent material that he coated his screen with. By the way, a phosphorescent screen is something that will glow if it's kind of energized, and it will glow, it will not just glow and then go out immediately. Like, it's not just while you're zapping it with some energy that it glows. It actually takes a while to discharge itself, so get a little bit of a glow. So here's what he did. So the cathode rays are coming from the cathode. Big high electrical potential, big high voltage between the cathode and the anode. So something is happening. There's a big electrical discharge. Whatever is flowing from the cathode toward the anode is flowing. Okay, and you see the little slits there in the anodes. Those are called collimating slits. They're little slits that allow just the electrons that are pretty much headed straight down to get through. Okay, and then these magnetic and electrical fields are designed so that when you tune them both in, so that you get the phosphorus screen display a little dot right dead center in your little screen, you can take the dial, you can take what you've you can measure, the dial would determine the size of the magnetic field and the electrical field that you were applying, which affects charged particles, and you could tell what the ratio of the mass to the charge for whatever the thing was that was making up those cathode rays. Okay, and so he expected that he was going to find, like a hydrogen atom that was charged or something like that when he had a trace gas of hydrogen in his tube. Although, by the way, his experiment depended on a very, very good vacuum because he didn't want he wanted to have very clean results. Once he got these cathode rays happening, he didn't want them hitting ramming into little bits of trace gas on their way to the screen. He wanted to be able to control. So he had a pretty high vacuum, and yet he did have a little bit of a trace gas. It wasn't a perfect vacuum. He was expecting he was going to find atoms. He was going to find little pieces that the mass to charge ratio for those pieces would be kind of consistent with atoms. And he knew what to expect because Faraday, we didn't talk about this, but Faraday, who had helped Maxwell so much, was also quite the chemist, and he helped invent the entire field of what we now call electrochemistry. And he discovered, he discovered that there was a certain amount of current that had to flow to do electrolysis to get a certain amount of hydrogen out. And he was able to figure out, based on that, how much mass of hydrogen would correspond to a certain amount of charge, right, that had to be passed through the current. And Faraday was expecting to find that mass to charge ratio if he had encountered hydrogen, which was his trace gas. But what he found instead was something that was 2,000 times smaller. By the way, I also mentioned there in the little bullet points, Wien also have measured that mass to charge ratio for hydrogen. And so, but the main thing here is what J.J. Thomson found was 2,000 times smaller. So, he had actually discovered here the very first subatomic particle. These cathode rays were made out of these little tiny particles who had a very small mass to the given charge. Very small, much smaller than atoms. And yet they had to come from somewhere. And there's only one place for them to come from. They had to be coming from these atoms. So we've known about atoms since the time of Dalton, a couple of classes ago, but no one knew what atoms actually involved. We knew about static electricity. Well, whatever current is, whatever these charges are that J.J. Thomson is seeing, they have to be coming from the atoms. Normally an atom is neutral, right? Normally an atom is neutral, but when something gets static charge on it, a static charge, then you can actually see that. Also, Faraday was able to see that in his chemistry. He was able to see that like in a solution, you would get atoms moving in one direction or another under the direction of electric current. You could do things like electrolysis, or you could do silver plating, or things like that. Okay, so Thomson knew that this thing he was seeing was so small, it was way smaller than any atom. It had to be just part of an atom. That had to be the charge that was flowing there. And so eventually this subatomic part that he came up with was called an electron, and it was the very first subatomic particle discovered. He won the Nobel Prize for this work. Now, before we rush off from Thomson, I just want to say that this device he used for his basic research was exactly like CRT tubes or television tubes that were to come. It worked pretty much the same way. Okay, I mean, they got more and more refined over time. They got fancier and fancier. I won't even talk about color TV. But this was the great grandfather, or maybe the grandfather of television and computer monitors and all that stuff before we had the flat screen technology. So that's kind of interesting. You can see how science continually has the spillover effect into the technology experience as part of everyday life. Now, Thomson had figured out the mass to charge ratio of an electron. And so it had only about 1/2000th of the mass of a hydrogen atom compared to the charge of a hydrogen atom, say, from Wien or from Faraday. But that ratio didn't tell the actual mass of the particle. Okay, so one person who was able to gain some insight there was Millikan. He did a very celebrated experiment now to try to put it together, and it's remarkable. What he did was he figured out that if you took an atomizer, like something that was very perfumed, but instead you put some kind of oil in it, and it was a particular kind of oil in his case, he studied the little droplets enough to know that the amount of oil in a particular drop was exactly could be exactly related to the diameter of the drop. So when you atomized a little bit of oil, some of the little drops would be bigger, some would be smaller. Okay. Now here's another thing he noticed, that if you use an atomizer, just like when you rub a comb through your hair, sometimes you can get a static charge. When you squirted these little oil drops out of an atomizer, a lot of times just the process of squirting them out of a nozzle created a little static charge on these little oil drops. Okay, so this guy was smart enough to figure out that, hey, I can use that. I can use an electric field, right? That's going to, because an electric field will affect charges. It will attract or repel charges depending on the charge. And he could tune the electric field to hold certain drops suspended in size. Okay, so whenever he cranked up the electric field enough to hold certain drops of oil in place, and he could see that, you can see the picture of his device on the bottom. He had a little telescope he could look through. He could actually watch a drop, and he could kind of dial his electric field into place so that it held it suspended. Then he knew how much force the electrical field was applying to that drop. He also knew how much the drop weighed. This was all in a vacuum. He also knew how much the drop weighed and how much gravity was pulling it down. So between the two, he was able to figure out how much oil was in the drop. So he was able to figure out the charge, based on the amount of force needed to balance the gravity, and he knew the mass from the size of the oil drop. So, and what he discovered is there was a particular charge value, and so a little oil drop could have no charge, or it could have one multiple of that charge, or two multiples of that charge, or three multiples of that charge, depending on things. But it seemed like you couldn't have fractions. So what he figured out was, hey, when an oil drop gets a negative charge, the least charge that I'm seeing here for any of my oil drops, that must be the fundamental drop or charge that J.J. Thomson saw. And so, given the fact that he knew the mass of the oil drop and the size of the charge, then he was able to determine, he knew the absolute size of the charge, and when he knew the absolute size of the charge, that meant he could figure out the absolute mass of the electron. And indeed, it turned out to be only 2,000th of the size of a hydrogen atom, basically. Okay, so here's the thing. At this point, if we look at the picture on the left, this shows one of our loose ends that we're trying to resolve. During this era, people were increasingly using electricity, but they had no idea what electricity was. They knew that there was some sort of flow of charges through a conductor and that it could do work, but they didn't know what it was. That's why we have the question marks. Now, between J.J. Thomson and Millikan, we're able to say, we know what's flowing. It's electrons. They're negative charges. And actually, the flow is in the opposite direction that we thought for current. So you'll see my arrows on the right are reversed. But the point is, now electricity is a lot more understood. We know what's flowing, right? Those are electrons. We know why they're flowing because of an electric field, because there's electrical forces resulting from the Coulomb force. That we already knew. We knew some kind of charge was flowing, but now we know what is making up the charge. So that was the first discovery of what we call a subatomic particle. So knowing what electricity was, that was great. But scientists were very excited about having a better understanding of the atom because everything's made up of atoms. The better you understand atoms, the better you understand everything that's built out of atoms, which is everything. Okay, so electrons clearly didn't weigh very much. The very lightest element is hydrogen, and an electron weighed only 1/2000th of a hydrogen atom. So there had to be something else in those atoms, right, to make up the difference. So what about the rest of the atom? That was something that scientists really wanted to understand. Well, we have some clues. If we look at our periodic table, and we haven't spent a lot of time talking about it, we know that Mendeleev started putting it together, and it was arranged from lightest to heaviest elements, so that from left to right and top to bottom it got heavier, but also arranged so that in individual columns you had elements that had similar chemical properties. And this is the shape that kind of came out. So basically there's something called the atomic number on the upper left hand of each square, and for now we can just I'm sorry, that's not the atomic number. The number is the bottom center, and for now we can just take that to be the order in which it appears in the periodic table. Whereas at the top left we have a relative weight. When chemists figured all this stuff out, starting from the time of Dalton, they could tell what the relative weights were between the different kinds of elements in chemical reactions, and so they knew that hydrogen was the lightest element that they had seen. They knew that lithium, right underneath it, which is the third element in the periodic table, they knew that each lithium atom weighed 6.9 times as much as hydrogen. And then the fourth element in the periodic table, like beryllium, they knew it was number 4. It weighed 9 times as much as a hydrogen atom. But the first clue, but this is the clue that I want you to follow along with. Whatever atoms actually were, their masses always seemed to be approximately some whole number multiple of the mass of hydrogen. At least until you got up to around chlorine. And then it's right smack dab in the middle of 35 and 36. So you can't call that close to an even multiple of hydrogens. But it held until then. But still, clue number 1 holds well enough so that it was interesting. And for most elements, even after chlorine, it holds pretty well. So that was one clue. Here's another clue. Kind of discussed this before. When we interact with things normally, they don't have a static charge. They aren't attracted or repelled to other things with a static charge. Instead, they're electrically neutral. So we know if electrons are coming out of those atoms, and that's what the charge is flowing through a circuit, we know that normally for atoms to be electrically neutral, there must also be some positive charges somewhere so that they add up to 0. Okay, so that's clue number 2 about what the rest of the atom might be made up of. Then here's another clue. Now that we know electrons are the things that are traveling around the circuit and streaming during electrical discharge, we can, and now that we also know from Thomson and Millikan that they're very, very light, much smaller than atoms, so they're mobile, right? Well, that's another clue. And that enabled people to come up with a lot of different uh, conjectures about what atoms might look like inside. So on the left, we have something called the dynamid model. Now, the dynamid model was proposed basically because, okay, if you suppose that you must always have, for a negative charge, you must have a balancing positive charge, right? The very simplest atom, hydrogen, the very lightest atom, uh, would, well, let's suppose it would have one of each. That's the simplest thing we can imagine. We wouldn't have known that at this point, but let's suppose it. So maybe a hydrogen atom we can think of as a little negative charge and a little positive charge kind of stuck together because they would tend to attract. And then maybe since heavier elements, like lithium and beryllium and so on, maybe those just have multiples of these little negative, positive charge pairs composing them. Okay, and those little building blocks, the negative, positive charges, they were called dynamids. Okay, so that was one conjecture. Okay, now there was another conjecture, and these are all notable. There were, I'm sure, endless numbers of these things and variations. Another conjecture about what atoms might look like was called the Saturnian model. And here's the idea there. If electrons flow so easily, okay, then maybe there are lots of little tiny electrons, very, very tiny, which, J.J. Thomson and Millikan had found that they're very light, and maybe they ring the atom kind of like the rings of Saturn go around Saturn. Okay, so they just spread out in a ring around a big offsetting positive charge. So maybe there are thousands of electrons around each atom. They think each one very tiny with a very, very small charge, and maybe there's a big charge in the middle, and maybe these charges kind of just go around. The negative charges just go around the charge in the middle, kind of like the little pieces of ice and stuff making up the ring of Saturn. Rings of Saturn, they orbit the planet Saturn. So the positive charge in the middle would be much bigger than all the individual little electric charges, but they would still balance. Now, this was a good model insofar as it would explain why electrons would flow so easily, because they were way outside the atom. They would be the thing that could be easily picked off, and at the same time, there's another thing we have to consider from Maxwell's equations, which is anytime you have a charge that is being accelerated, which would include being forced to go in a circle by another charge like this, you actually would get electromagnetic radiation. It would actually create like some sort of radio wave or something, right? Even if they're just little charges, they would kind of count as a circuit, kind of like a circuit loop, and they would, and because there was acceleration in the charges. But the Saturnian model said, hey, if the charges are so uniform, the electric field wouldn't actually be changing. The individual particles would be moving, but the ring itself would be kind of fixed, and it wouldn't have to give off electromagnetic radiation. And so you can have it outside the heavy part of the atom, orbiting, where it'd be easy to kind of flick off and be part of a electrical circuit, flow through a conductor or whatnot. But it would explain why you wouldn't have to have the atom also giving off electromagnetic energy, right, as part of a radio wave or some other kind of electromagnetic radiation. Because if the atoms did give off that other energy, then the atoms would quickly have to collapse. And we didn't see that. Atoms seem to be pretty persistent. Things stay around. Okay. Now there's a third model, and this was come up with by Nobel Prize winner J.J. Thomson. He called it the plum pudding model. and he's British, so we have to allow for his notion of a pudding. It's more like what we would call a muffin. And when he says plum, that's kind of J.J. Thompson speak for what we would call a raisin. So his plum pudding idea of plum pudding is what we would think of as a raisin muffin. And so he thought, okay, hey, maybe the little electrons that flow so easily, maybe they're like the raisins on a muffin. You could just kind of snag one off. They could easily get taken away from the muffin. Um, but the bulk of the muffin that the raisins are in, um, that's the rest of the atom. Okay, so the electrons are like the atoms, and the thing they were in, what we would call the muffin, that was just some kind of positively charged substance, and that was a total gas. So none of these really seem very compelling. They are guesses, so clearly we need more info. Meanwhile, fortunately for us, back at the ranch, um, we can segue to a guy named Wilhelm Röntgen. Okay, he used a very similar device to J.J. Thomson, but we're gonna look at his story because it ties into a whole other thread that we need to talk about. So his device was kind of sketched out in this little diagram here that says EHT. Now, this is not specifically his device. This is a more modern version. Um, but what he did is something very similar to what J.J. Thomson did. He had a cathode, big electrical potential difference or voltage applied between the cathode and the anode, caused electrical discharge, and his arrangement would generate X-rays. Okay. Um, Now, his X-rays they were electromagnetic radiation. They were the kinds of things described by Maxwell's equation, like light, but something we couldn't see. And this particular electromagnetic radiation was high energy. Okay, so he found accidentally that his Crookes tube with this sort of arrangement could actually see right through you. These X-rays could actually see right through you, and you could expose film to it, and you get a picture of someone's bones. He actually had a screen coated with some sort of phosphorescent material that he could put his hand in front of with X-rays coming out of his Geissler tube kind of setup, and he could see his hand, or it's more of a Crookes tube type setup. But in many ways, it was a lot like a Crookes tube, or even a J.J. Thomson model here had the same kinds of pieces, but it gave out X-rays. Now, it should be mentioned, just in passing, if you guys notice, there are some little lightning bolts, bluish lightning bolts, back up around Thomson's cathode ray tube, and remember, that's kind of like our old television tubes. And I don't know if you were ever told not to sit in the back of a TV because it gave off X-rays. It did. Fortunately, home X-ray never became a thing. So, but it wouldn't have been a very good. Your old TV sets would have been a good X-ray anyway because they didn't give off that many. Röntgen's arrangement was optimized to give off good, strong X-ray beam. It had to do with the type of material the anode was made out of. It turned out if it was a heavy metal type of material that it would generate these X-rays. Well, Röntgen's X-rays were absolutely fascinating to people at the time. They were captivating to scientists, and because of their behavior, they kind of started being discussed along with some other things that are generally all described as radiation these days. So I want to take a step back from the period of history we're talking about, which is the beginning of the 20th century. And I want to just kind of step out of that and talk about terminology, you know, um, from our fully informed 21st century point of view, just to help make the terms a little clear. Okay, uh, and then we'll go back into our story about how things developed. But um, anything technically, anything that radiates outward or travels outward could be called radiation, even in a poetic sense. But normally, when we talk about radiation, and this is true um, since the beginning of the 20th century, normally when we talk about radiation, we mean one of two things. We mean either electromagnetic radiation, like what's described by Maxwell's equation, including light, or we mean little subatomic particles, which in our story we've encountered only one of so far, the electron. Okay, we mean one of those two things. Okay, now when we talk about electromagnetic radiation, which can always be called electromagnetic radiation, we typically only call X-rays and gamma rays, which are on the right. Those have very short wavelengths, very high frequencies, and have lots and lots of energy. And they can do harm to our bodies. Okay, um, X-rays and gamma rays are able. They're so strong that if they hit, you know, um, like a person or an animal or a life form of any sort, or even a rock, they are able to strip the electrons right out of there. And so they can completely rip the electrons away, right? Completely rip the electrons away. And that can cause, in living things, that can cause genetic damage, which eventually can cause cancer and that kind of thing. It's not that there aren't some good uses for these things, but they can cause harm. We call that ionizing radiation. It's able to take the electrons right away from the atoms altogether, and so they're pretty severe. Now UV light, the ultraviolet there at the top three from the right, the ultraviolet light is also very energetic. It cannot ionize for mostly. It doesn't ionize atoms. It doesn't rip the electrons right off, but it can add a lot of energy to atoms and cause unfortunate chemical reactions to occur on your skin and things. Typically, it doesn't penetrate very far, but it can cause chemical damage on your skin. Okay, so it's a little harmful. Every now and then you hear it referred to as UV radiation. Usually we don't, even though it can be referred to as radiation, we don't usually refer to visible light, infrared light, um, or even radio broadcast as, radiation. Although the word still technically applies, but as in terms of usage, we don't say it that way. Microwaves are really, in terms of danger, not as dramatic as the things on the right, but they can transfer heat just like infrared rays, and it's true that they could do damage. I mean, so maybe some people refer to microwave radiation sometimes. Um, well, the other type of radiation has to do with particles. Okay, um, we've encountered the electron. We're going to find out that those are beta particles. If you see the second listing down on the bottom half of the screen, the little funny bee looking thing, those represent beta particles. Those are really going to turn out to be electrons. We see that X-rays and gamma rays are also listed down here, although they're not particles, but they're very often thought of as radiation. And we see two others, alpha particles and neutrons. But we're going to sort all those out today. Alpha particles, beta particles, and neutrons are all what we call subatomic particles that have energy and can do damage. And so they are referred to as radiation, um, but technically that applies to electromagnetic radiation as well. So hopefully I've tried to straighten the terms out a little bit, and the key thing is just remember that radiation can be two things. It can either be something like light, but at a different wavelength, maybe a higher energy, or it can be something like little subatomic particles, things that can make up atoms that fly around and can do what they do. Okay, so that's our discussion there. So let's go back into our story. So the first hints of radioactivity, what was being called radioactivity by the time Roentgen discovers his X-rays. The first hints of radioactivity of either type um, came about much earlier, from around, oh, I don't know, probably 1870s or something like that. There was a photographer, and I'm just going to call him uh, Saint Victor because that's his last name. There was an early photographer, French guy, and he studied how to prepare film from a lot of different types of materials. It was an interest of his. Okay, um, and he was also a military guy, so he had military reasons for wanting to make better film. But he was a photographer, and he was trying to study different approaches to making film, and so uh, at his point in history, basically film was made out of these chemical emulsions prepared from certain metal salts. Now, I'm not going to explain what that is chemically. It's just they would include things like silver chloride, right, or other kinds of metals and halogens, things from the right side of the periodic table. Um, so that's not really the key we need to understand. I mean, we don't really need to understand that, but he wanted to experiment with metal salts. So by this time, the element uranium, which was the heaviest known element, existed in nature in all kinds of different forms. And a lot of these forms were salts of uranium, chemically speaking. So instead of silver chloride, you could maybe have uranium chloride, or actually more complex salts than that. But he was interested in seeing if any of these uranium salts would make for good film. And so he found something very interesting. When he went through the steps of preparing an emulsion, which is just like an even spread of the chemical in some sort of like little gel, right? Uh, when he used uranium salts, um, they darkened themselves. Even if you didn't take a picture, they would end up darkening, and so they were useless as film. Okay, now this guy Saint Victor, he was aware that there was a famous French scientist that during his day was working on fluorescence and phosphorescence. Okay, his name was Becquerel. Okay, and so he knew about Becquerel's work. So Becquerel um, was working on things that were fluorescent and phosphorescent, and it so happens that a lot of things in nature that are fluorescent or phosphorescent, especially fluorescent, I'll say fluorescent, a lot of things in nature that are fluorescent happen to be these same uranium compounds. And by the way, a number of the different ores of uranium, or different crystals with uranium salts, are shown at the bottom. He knew he happened to know, St. Victor happened to know that Becquerel was studying fluorescent uranium compounds, among others, and so he thought, well, gee, maybe this, what I'm saying, maybe it's because these compounds are like phosphorescent. Maybe they're glowing a little bit, and that's why they're darkening their own film. So it was kind of a reasonable thing to suppose. Um, Now, the way phosphorescence worked is something that's phosphorescent, like you could put it out in the sunlight, it would soak up the sunlight, and maybe it would glow for a fairly significant period afterwards. Okay, so he actually tested this out. He made his film. Well, he had made his film before and saw that it self-darkened, but then he made sure that he kept his uranium salts in the dark and made his emulsion and everything so that in no way would they get charged up so they would be expected to glow like a phosphorescent or compound later. Okay, and then he made the film just to see if that made the difference. And you know what? Even if he hadn't exposed those materials to light for 6 months, they would still darken. The photographic plates he had created would still darken themselves from the uranium salts. So he speculated that this was something new. He speculated that the uranium salts were putting out some sort of invisible radiation, you know, kind of similar to electromagnetic radiation, but something that could not be seen or was not even that kind of thing. Okay, and that something was coming from the uranium salts that was darkening the film, and it was something that was new, a fundamental discovery of a new thing. And he was right. He wasn't given any credit for it. He's almost a footnote in history. It would have to be rediscovered. So we continue ahead, and eventually we get to this French scientist Becquerel, who rediscovers what St. Victor knew some years later in 1896. Even though St. Victor was aware of his work, he knew nothing about St. Victor. He basically rediscovered in 1896 what St. Victor had found. Okay, so he had long studied these sorts of materials that were fluorescent and phosphorescent. And here's the thing: even though X-ray machines had only been coming out for a few years at this time, there was an American called Elihu Thomson who was already commercializing X-ray machines, and he discovered that the heavier metal the target was formed out of, the better the X-rays. Okay, so Becquerel was aware of that discovery. He knew that the target of the X-ray, if it was some very dense metal, like tungsten, right? He knew that gave the best X-rays, and he wondered if there was any connection between X-rays and like phosphorescent, like luminescent salts of uranium, salts of uranium that could glow. He wondered if, because uranium was not just a heavy metal, but the heaviest of all metals, he wondered if once it stored up sunlight, he wondered if maybe it would give off X-rays. Okay, now this is kind of a leap in the dark. I mean, you can kind of see how he was motivated, given how heavy uranium was. So he was able to, one way or another, grow some uranium sulfate crystals in his lab, and he prepared film, probably much in the way that St. Victor did, and put it on plates and everything. And he was going to expose. What he was planning on doing was this: he was going to take the film out, and he was not going to expose the film, but he was going to put the uranium sulfate crystals on the film in the sunlight. So the sunlight was going to hit the uranium sulfate crystals. He was hoping that then those crystals would start to phosphoresce, to glow, not in visible light, but in X-rays, like the sort of X-rays that Röntgen had discovered, and that those X-rays would, because they were X-rays and they were understood to do this, they would pass through the packaging and everything where the film was sitting underneath the crystals, the material that was keeping them from being exposed directly to light, and they would cause the film to expose and illustrate that that you know, because X-rays were already seen to be valuable, he thought this would be a tremendous property of uranium crystals if they did that. Unfortunately, after he did all his prep work, it was cloudy, and so he just threw his film that he prepared in his desk, and he put his uranium sulfate crystals on top of his film in his desk without exposing any of them to sunlight. And you know, I guess he didn't get to do his experiment, and then the film got to be old, and it was too late to use them because this type of film didn't last forever. And so, on a whim, he decided that he would develop the film anyway, although you know, he didn't have any great reason for doing it. He thought there was probably very little point. It's just it was already wasted. So he developed the film. And what he saw was that the uranium sulfate crystals had darkened the plates. You know, you could actually see their picture. So they did not need to get hit with sun. They did not need to soak up any light in order to give X-rays off. They gave the X-rays off regardless. And actually, wasn't X-rays. It turns out to be something else entirely, but he thought it was X-rays. So at this point, well, actually, even at this point, he's realizing, hey, this is something different. This is something new. He wasn't sure what it was, right? He wasn't sure what it was, but he had recreated what St. Victor did. And it was a fundamental discovery for which ultimately he would win the Nobel Prize. But he did take it one step further. He wanted to see if maybe it was something other than X-rays, because he was a physicist, and so he set up the situation again, except he put some magnets in place, and he found that the magnets were able to shift the images on the film in a way that indicated whatever was coming from these uranium sulfate samples, they must have, at least some of it had to be charged particles. But in the end, he figured out that some things were positively charged, some things were negatively charged, or some things were not charged at all. He could see all the different ways that the photographic plates were being affected. And eventually, you know, in 1900, which is 4 years later, and I think just a couple of years after J.J. Thomson's experiment, he found out that the negatively charged radiation was in fact the very electron that J.J. Thomson had discovered. But there's a different thread in the story, so we're a few years before that right here. Well, at that point, we're continuing to follow in the thread of radiation here. We encounter Pierre and Marie Curie, French couple. Both of them are physicists. She is a rare woman physicist. She's jumped every hurdle. She was an immigrant to France. You know, she had to fight for the right to pursue research and her studies and everything, and ended up being the only human being who's ever won 2 Nobel Prizes in 2 different hard science fields. Okay, so she was quite impressive, but Pierre was not too bad either. Pierre and his brother Jacques was also a scientist, had discovered something called piezoelectricity earlier on, before he was married to Marie. And that's basically where, if you apply pressure to a crystal, for example, a quartz crystal, and this is the heart of every quartz-based timekeeping device these days, not to mention it's something used for airbags and all kinds of stuff, but if you put a crystal under pressure, you can actually generate small electrical currents. And as part of that work, Pierre and his brother Jacques had to create a very sensitive device to measure electrical charges, kind of like our you know, electroscopes from before, but much more sensitive. So Marie was working on her doctoral um, paper, thesis work in physics, and she had chosen radioactivity, which was a new and exciting topic. It was kind of wide open, and she decided that she would use her husband's very sensitive device, which measured charges, to see if perhaps um, uranium samples, like uranium salt samples, like those encountered by Becquerel, would possibly um, cause chemical ionization of the air, which chemists understood. They saw all kinds of things happening in solution that she could detect with her very sensitive device. Okay, and so she did, and she found out she could detect it. In fact, um, she was able to create a situation using um, what she knew about her husband's work in piezoelectricity. She was able to create a situation where she would stress a crystal to generate an offsetting current compared to the current that was caused by the ionization of the uranium salts in the device. I know that sounds like a bunch of gobbledygook, but she was able to basically count. Um, she was basically able to keep track of how quickly the uranium salt sample was building up ions in a little chamber that she was using to measure charges. And she found that the rate seemed to depend only on the amount of uranium. It didn't matter what the source of the uranium was, no matter what the ore of uranium was. It only depended the rate at which the, the air was being ionized by the sample for a given amount of sample depended only on the amount of the element uranium in the sample. So it was if it had a lot of other stuff in the sample, like chlorine or other elements that made up part of the sample, they wouldn't contribute to the radioactivity. And so it did the chemical nature of the sample didn't matter, just the presence of the uranium did. And so she decided that, or she inferred that this radiation was coming from the uranium, not as a result of a chemical process of any sort, but it was coming from the atoms of uranium themselves, which of course she was right about. Um, but then as she studied more and more, she eventually got to the type of material on the right, which is a uranium crystal called torbanite. It's not a mineral, and torbanite was different. It broke her rule. She found out that torbanite was more radioactive than uranium itself. So even if it had been 100% uranium, it created more ionization in her little measuring device than pure uranium. Okay, so there had to be something else in that torbanite that was also like uranium, giving off radiation. By the way, her way of measuring things, eventually similar principles get incorporated into what we call a Geiger tube, which can even be portable, and you can walk around and measure radiation and stuff. But let's continue with her story. So torbanite turned out to be 2 times as radioactive as pure uranium of the same mass, and then even more so, there was a really ugly kind of well, I guess you could call it ugly or fast or interesting, depending on your point of view. There was something called pitchblende that was known to contain uranium, and it was of no interest to Becquerel at all because it did not exhibit any sort of it didn't glow under light or anything. Okay, so there was no sorts of there was no sorts of luminescence or phosphorescence there. No fluorescence or phosphorescence, but it also contained uranium, and it was 4 times as radioactive as pure uranium, torbanite twice as radioactive. So she figured, hey, there has to be something extra going on here that's even more, there has to be something in here that's even more radioactive than uranium. So, she starts to use every technique at her available. She crushes up the samples, she uses chemistry to try to isolate the different types of elements in a sample. And if you're doing all that kind of stuff manually, it's very hard to do. It takes a lot of work. And so eventually, out of torbanite and pitchblende, maybe one or both, I'm not sure which, she comes up with the element thorium. Now, this element wasn't an unknown element; it was already on the periodic table. So, and she found it was indeed radioactive. So that was the second element known to be radioactive after uranium, but it wasn't as radioactive as even uranium. Okay, so it was not explaining why the torbanite and the pitchblende were so much more radioactive than pure uranium. So she kept at it, and she found traces of another new element. Okay, now she was originally from Poland, and so she, in honor of her country of origin, she was she discovered the element, so she was allowed to name it. She named this new element polonium. Okay, and it was more radioactive than uranium by a factor of billions. Okay, so there was just a little bit in the pitchblende, I think it was, but it was enough, right? It was enough to increase the radioactivity of the sample. Okay, and once she had concentrated it chemically and isolated it and studied it, um, she was able to measure that it was in fact billions of times more radioactive. And she continued to look, and she found another new element named radium. So polonium and now radium. Neither of those were even known elements until she found them in these ores, and it was also much more radioactive than uranium by a factor of millions. Okay, it was millions of times more radioactive than uh, uranium, but not nearly as radioactive as polonium. Now, uh, because polonium was so radioactive, the sample kind of, something that wasn't immediately understood at this time was that when radioactive samples decay, and she eventually studied all this stuff, when radioactive elements decay, they turn into other elements. Like when you have polonium giving off radiation, it turns into something else. So it's so radioactive that it changes so quickly that it's hard to have much of it. It takes a long time to isolate it from your pitchblende, and then you don't really have much longer to work with it before most of it goes away. But radium, which is pretty radioactive, um, but not nearly by the same factor as polonium. Radium ends up being useful in research, and it's a metal. Okay, on the periodic table, it ends up fitting into a column that you would expect for a metal, and she continued to work with that until she was able to isolate it as an actual metal in 1910. Before that, she had radium chloride, and that was still useful in many ways. So she, as much as she could, she figured out the chemical properties of all of these new elements so they could be put on the periodic table. She also noticed that radium could be used in a constructive way to kill cancer cells because radium would kill cancer cells faster than normal cells, and so it would be one way for fighting cancer, although it wasn't good for the normal cells either. And eventually that would become clear later on. Okay, she was awarded her second Nobel Prize for isolating these elements. Um, that was in chemistry. The first one was shared with her husband to discover, for her work in measuring radioactivity in the first place. Well, now we go back to England, where J.J. Thomson was working, and we encounter uh, Rutherford. Ernest Rutherford, and he was interested in her work, and so he had some uranium samples, and he did some experiments himself. Okay, he found, and he was using a similar way to measure the charges that she was using to measure her charges. So he was able to measure the radioactivity in the same way, and he discovered that if you put thin layers of foil over the sample, that the number of rays that were coming out of it, the radiation that was coming out of the sample would drop kind of proportionately. So, ever how much it did until a certain point, and then it wouldn't drop anymore. So what he thought he was looking at was a situation where, hey, more than one thing is being given off by these uranium samples, okay? And the things that were being stopped by enough foil, once you had enough foil, right, he called alpha rays. I think he knew that they were positively charged, okay? The things that went on through anyway, that weren't stopped by the foil, he called beta rays, and those turned out to be electrons, and they were negatively charged. At this time, he did not know about the gamma rays being given off by uranium. Those are electromagnetic rays that are also, that are given off, not particles. We would say not particles, but actual electromagnetic rays of very high energy, beyond X-rays. He didn't find those at this time. Later on, he would encounter them, and he would measure their wavelengths, and he would give them the name gamma. So he called these common types of radiation alpha, beta, and gamma rays. Well, as an interesting side note, since this is a Science and Christianity class, I believe his father was a pastor, if I'm not wrong, but Rutherford made an interesting comment about this time, around 1904. There was a famous scientist, Lord Kelvin, as he was known according to his title, or Rumsford, and we talked about him, who had said that one reason not to believe in an old Earth is because there were no known energy sources that would last long enough to continue to produce energy all that time. So whatever powered the sun, he was basically saying, hey, the solar system can't be that old; it would have burned out already, as far as what we know. And Rutherford observed, as he started working with these samples, that radioactive decay, something about the energy in an atom, it might actually be able to provide a much longer lasting energy source. So in passing, that's what he observed. But let's continue, because Rutherford continues with his work. And Marie Curie, in the early 1900s, had supplied him with radium. So no longer is he working with just uranium. And he's very fascinated in this whole area. He knew that a lot of these ores were found with trapped helium gas. And so he knew that alpha particles were positive, and he speculated that maybe these alpha particles are ionized helium gas, right, atoms, and maybe they'd had their electrons stripped away, right, because they're positive, so it's positive. And so he does something very clever. Okay, what he did was he created a little glass, double-walled glass chamber, and one side of it was very, very thin, okay, and the other side was very thick. And he knew that the alpha particles would not be able to pass through the thick wall, but they could pass through the very thin wall. And so basically he aimed alpha particles into this little chamber, glass chamber. They passed through the thin wall and they got trapped by the thick wall, and they couldn't they couldn't come back out, so they were stuck in the little section between the two walls. And then later on, he went back and he checked, and he found actual helium had been deposited by those alpha particles. He even took the gas and he verified the spectrum that it gave the expected result for helium. So that was a pretty exciting discovery. So now we know that the beta rays were electrons, and we know that the alpha rays are the same as helium atoms that have had the electrons stripped off. Apparently, once they, get trapped by the glass, they grab onto a few electrons from the glass, and actual helium atoms are found. Okay. Now, in 1908, he also did an experiment. I went too fast there. With Geiger, who eventually invented the Geiger counter, and he's able to measure how many um, little hits he has on this screen that he had coated with some phosphorescent material. So he's pointed his alpha, he's got a little radium sample and he's letting it generate alpha particles and hit the screen. And so he's able to tell how many times the alpha particles hit the screen, but he's also able to measure how much charge accumulates. And so he finds out that these alpha particles, which he knows are helium atoms minus at least one electron, they actually are missing two electrons because they have a charge. The particles themselves have the charge, double the charge of an electron, except it's positive instead of negative. And so about that time, he was recognized with a Nobel Prize in chemistry in 1908. But it was not even his most remembered result. His most remembered result is what he later did with his radium. He basically saw these alpha particles as like little cannonballs that he could shoot at atoms to see what happened. And so he was maybe the first guy in physics to take the approach, hey, let's just shoot at the atoms and see if we can pick up the pieces and figure out what happened. Okay. It's kind of like on a crime drama these days, if you have a crime scene where lots of bullets are on the wall, you can kind of trace it back and see where the shooter stood and determine some things. So that was basically his approach. And so here's what he did. He took his little sample of radium, he put it inside a lead box that had a hole, and he let that pass through the hole, and he aimed it at a sample of gold foil, which he had worked with before. And then he had a little screen that was coated with this phosphorescent material that kind of circled the gold. Okay. And so what he did was basically he was shooting his little cannonballs, his alpha particles, at the gold foil, and he was going to see where the cannonballs bounced off to, kind of like where the bullets hit the wall in a crime scene. And, from the geometry and the math of it all, which you can kind of see down to the right, he was going to see if he could figure some things out. What he really wanted to do is probe the nature of the atom. And here's what he said from the results. Because what he was expecting, according to his mentor, J.J. Thomson, was that the atom was kind of like plum pudding, or we would say raisin muffin, and the electrons were kind of just scattered out, and the atom was kind of distributed out, over the entire amount of space the atom took off. And he was thinking the alpha particles, would be approaching a fairly neutral atom, and electrically neutral, where the positive and the negative charges kind of canceled out, and only as they got close to individual charged portions of the atom in the plum pudding model would they be deflected maybe a little bit. Okay, so that's the Thomson model of the atom, to the right of the device there. What he found was something really different, and so the results were stunning. This is his quote. It's a fairly famous quote from his, how he felt. He said, "It was quite the most incredible event that has ever happened to me in my life. it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So in his mind, these alpha particles were like some ballistic missile or some cannonball, and he was hitting something that was so lightweight and not very dense that he just expected that the thing would go right through. But in fact, he found a lot of them bounced back or had severe angles, and he was able to work out that the atom was far from what his mentor Thomson had thought. The atom had to be very, very densely concentrated in some sort of nucleus. Now, atoms were known. Chemists had figured out the atoms were somewhere on the order of, you know, 0.000000001 meters wide, okay, which we call 1 angstrom. And yet, for this behavior to happen mathematically, almost the entire mass of that atom had to be concentrated in a little nucleus of some sort, a little dense area of some sort, whose radius was 10,000 times smaller than that. So in other words, the atom had to be almost entirely concentrated in 1/1,000,000th of the volume of an atom. So, and it had to be positively charged. So it appears from the Rutherford experiment that the atoms of the atom were way, way outside, 10,000 times as far away as the radius of the nucleus, and the nucleus is where all those positive charges were bound up. So this became kind of the new experimentally determined Rutherford model of the atom. So the electrons were thought to circle because, they can't just be out there. I mean, they would be attracted to this positive nucleus. So the only way they could remain outside to give the atom its known size, according to the chemists, the only way they could remain out there is just like the planets circle the sun. They had to be orbiting about the positive nucleus, and this is close to the picture that most people think of when they think of what atoms are. Little electrons whizzing around the nucleus in the center. And of course, the nucleus in the center, for the atom to be electrically neutral, would have a positive charge that would be the same size as all its electrons added together. They didn't know what the nucleus was made of, but this was his picture of the atom. And the nuclear age is born. So he discovered with this experiment the nucleus. Because of this and because of other discoveries that he made downstream, and also his students who worked under him, he's considered the father of nuclear physics. He also did more and more work. He had, as I say in the title here, he has other mountains to climb. So here's another thing he tried to do. Again, he decided to shoot up something with alpha particles to see what happened. It worked for him in his earlier experiments. So this time he shot alpha particles into nitrogen. And he was able to determine that sometimes when the nitrogen when an alpha particle hit a nitrogen, the nitrogen would absorb the alpha particle, and it would give off another kind of radiation, but it would, in the process, be transformed into oxygen. So this was something that he was able to see in a device that physicists invented and was very valuable for many years doing research, maybe still is, called a cloud chamber. You would typically create a situation where you had um, a super saturated uh, vapor. So, like for example, if it's like beyond 100% humidity on a given day, um, you know, the air just can't hold that much moisture, but it takes something to trigger the rain to start coming down, the rain droplets to form. It takes dust, it takes pollen, it takes something. The same way, physicists had like a volatile thing like an alcohol, but the vapors were super saturated, so it was like completely ready to turn back into liquid alcohol, and any little disruption would cause that to happen, and then you could kind of see the little droplets form, and you could kind of trace the path. So they were able to do that, and by doing physics like conservation of momentum and all that kind of stuff, they were able to figure out that you basically had an oxygen ion being formed when alpha particles slammed into the nitrogen. So um, it was oxygen 17, not oxygen 16. Um, um, if we looked at the periodic table, oxygen typically weighs 16 or so hydrogen atoms, but this is 17. Um, Chemists had discovered this concept of an isotope before. There was a chemist named Soddy who discovered them. But how can it be that you have the same element with a different weight? Aren't all these atoms the same? It wasn't really understood at this time why that was, but it was known that elements sometimes would come in slightly different weights. So this was O17. And so basically what you have here is a nuclear, not a chemical, but a nuclear reaction. You have nitrogen 14 being hit by an alpha particle, which is a helium-4 nucleus, apparently, and turning it into oxygen 17, and also um, a hydrogen nucleus being given over. So um, this is the first induced nuclear reaction, something that people caused to happen, that was detected and measured. Okay, and also this positive nucleus given off this one, positive charge that was equal in size to the negative electron's charge, but positive. It was given off in the process. Um, well, it was known to be the same as the hydrogen nucleus, which is what Wien found earlier when he was looking at the anode or canal rays. Uh, but at this point, what Rutherford recognizes is that you know this is something that was part of the oxygen atom, and now it's being given off, and it's the same as a hydrogen nucleus. Apparently, this is a subatomic particle, because hydrogen is the smallest thing we know as far as an element, the lightest thing we know. Maybe its nucleus is just one particle. Everything else seems to have multiple hydrogens and stuff in them. So this thing that's given off here, it's not just found in hydrogen, it's found in oxygen, probably every element there is. This must be a fundamental particle that makes up atoms along with the electron, and indeed that was right. So this is a second fundamental particle that combines to make up atoms. So you might, if you think about the situation we have here, so we've got the electrons circling around this positive nucleus in an atom. We've got the nucleus, for anything beyond hydrogen, having lots and lots of these protons very closely packed together, and they're all the same charge. Like charges repel. What's going to hold the nucleus together? Why doesn't what keeps why is the nucleus stable? Why doesn't it just explode? Because the electrostatic force is really pretty strong. I mean, it shouldn't be possible. There must be something more to the story. So Newton tells us that yes, the fact that the nucleus exists and has all these positive charges so close together means that there must be an even bigger force holding them together, you know, offsetting the repulsion. So now we have evidence for a new force, and it has to be even stronger than the Coulomb force between charged particles. So it came to be known as the strong force, a fundamental force of nature. And there's our character, the strong force. Yikes, he looks pretty strong. How can anything escape? Like alpha particles, because those are coming from the radium samples, right? Those alpha particles are coming from the radium. So if the strong force is so strong, why don't they escape? That turns out to be evidence, the first evidence for yet another force that can kind of work against the strong force, and it's called the weak force. Now, the weak force looks a lot less strong than the strong force, and it is, but it's still stronger than gravity by a huge factor. Okay, that's a story for different days. So the weak force allows nuclear reactions to occur. It allows radiation to occur. That's why it's got the little atom on it. The strong force is the strongest by far, though. And we still have the electromagnetic force out there and gravity. So here's our family of forces. These guys are all kind of brothers, okay? They're kind of bros here. We've got gravity. We've got the Coulomb force on the left with the little lightning sparks. We've got gravity, the weak force, and the strong force. And to our knowledge, these forces are the only fundamental forces in the entire universe. So these forces explain everything else in terms of how particles behave and relate to each other. So the four fundamental forces, and we now know what makes up atoms. At least we know a lot. We know electrons and protons are the charged particles that make up atoms. Well, Rutherford and others began to wonder something else. They wondered if maybe atomic number, you know, the order something appears on the periodic table, actually was the same as the proton number. If hydrogen had 1 proton, maybe helium had 2. But helium weighed in at 4 hydrogen atoms. So if it had 2 protons, then you would also expect that there's yet again something else that makes up the atom. There's another subatomic particle there. So the logic is kind of like, okay, if a hydrogen has just 1 of these things, and it weighs in at 1 hydrogen, and a helium is the next heavier element, and it weighs in at 4, well, in order for there to be a balance between positive and negative charges, chemically the next possibility, because the electrons seem to, you know, you would think that they would matter in the chemistry because they're kind of outside the atom, they can interact, which turns out to be right. So let's say that the next chemical element has, you know, 2 electrons and 2 protons, because why wouldn't that be the next one? Why would you jump to 4? Then that would mean that whatever was left over in the atom would have to weigh in at enough to give helium a weight of 4 hydrogens, not 2 hydrogens. And it turns out that there was a physicist named Moseley. He unfortunately died in World War I. He was able to give strong experimental results for this using X-rays. And the way he was able to do it is he basically showed that whatever, you know, he kind of reasoned that whatever orbits these electrons were in around the atom, that the electrons that were the closest in would be the most strongly attracted by the nucleus, and the amount of energy that it took to knock those electrons loose would only depend on how positively charged the nucleus of the atom was. And so he was able to show that indeed that that the atoms in the periodic table all had integer multiples of positive charge in their nucleus, starting with hydrogen and then sequentially going up by one each time. So he kind of found out that that's indeed how it works. So that meant there had to be another particle there, and it couldn't be positively charged and it couldn't be negatively charged. Well, either that or you had combinations of protons and neutrons that were canceling out in the neutron, but there was no evidence of that. So indeed, one of Rutherford's students named Chadwick, he found the neutron some years later. So it was neutral. That was a really hard thing to find because neutral particles weren't affected by magnetic or electric fields. But they ended up Chadwick ended up discovering the neutron by finding a case where there was some kind of a radiation that penetrated a barrier. It wasn't charged because it wasn't affected by charges, but it created a nuclear reaction away from, on the other side of the barrier that could be detected because it released charged particles. So he could tell that there was something shooting through a barrier that was neutral, which caused a nuclear reaction. So he was able to pick it up that way, and by measuring, the amount of energy in the other particles that were detected, and their, adding up their masses and figuring out conservation momentum and everything, using all the stuff from Newton, he was able to find the particle's mass. He had discovered the neutron, and it indeed was a neutral particle that weighed about the same amount as a proton. So back to oxygen-17, which was an isotope. As opposed to the normal oxygen atoms, you usually find oxygen-16. So if they have the same number of protons, that must mean it has an extra neutron, right? Yes. And that's how isotopes work. And now we can explain the atomic weight of chlorine on the periodic table or any number of other things. The reason chlorine has an atomic weight of 35.5, not 35, not 36, is it turns out that the weight that chemists measured was kind of an average according to the abundance. So mostly you have in nature chlorine 35 atoms, meaning 17 protons and 18 neutrons, but you also have enough chlorine 37, which is 17 protons, because that's what makes it chlorine, and 20 neutrons, so that the overall average, if you average them all out, you get 35.5. But each individual isotope of chlorine is also kind of an integer multiple of a hydrogen atom. Well, hooray, hooray. It's basically the picture of the atom we've been seeing everywhere since we ever looked at a junior high science book, starting from early in the 20th century until now. This is how people picture atoms. So it's a lot like the one we saw just before, the Rutherford model, except now not only do we have the electrons orbiting, but we have a nucleus in the middle composed of positive charges to offset the negative electrons, but also neutral charges called the neutrons. And it was Rutherford's idea that the neutral charges might somehow help to hold the nucleus together. And he was right about that, but it still involves the new force we introduced, the strong force. Sadly, this picture is not the final story. It's not actually correct. We're getting there, but it's not correct. I felt like at this point, quoting Ecclesiastes, "Vanity of vanity, says the vanities, says the preacher. Vanity of vanities, all is vanity." So it feels like we've gone this far, and we still haven't uncovered the actual nature of the atom. But we're getting there. Take heart. It may seem a bit discombobulating, but we are going to have to wait until next time to go beyond this picture. This picture is better than where we started. as much as we work to get there, because that's how the history unfolded, and it's something that's understandable, and will get us to the next level. Uh, but we'll have to wait till next time. And I haven't even gotten to the cat, and we don't want to offend the cat. So until next time, thank you for being in the class, and hopefully next week we'll pick up where we left off. All right, bye bye.